Probability, independence, and the multiplication rule. Let's start with a definition. We say that two events are independent if the probability of the first event does not affect the probability of the second event. If two events are independent, then the probability of E and F, the probability of both occurring, equals the probability of E times the probability of F. Now, even though part of this topic is independence, that is not the main point of this video. The big idea, which is true whether or not two events are independent, is the following. If we have multiple events, if we are choosing more than one thing, we will multiply the probabilities. That is what I want you to understand, because that will help us do a lot of probability problems, including this first one. So, for example, a florist has 10 roses, 20 carnations, and 30 lilies. What is the probability she randomly chooses a rose, puts it back, then chooses another rose? We say this is with replacement. So what is the probability of getting 2 roses? I could have written it like this: the probability of a rose and a rose. Notice that we are choosing 2 things. We have multiple choices. So we will multiply probabilities. The probability of a rose times the probability of a rose. You don't have to do the formality of this. You don't have to write this all out. Just remember to multiply. Now, a brief aside. This is not the same problem as if I said, what is the probability of getting a rose or a carnation? Now, I realize it's different flowers, but when I said it's not the same problem, what I mean is this. When I'm saying rose or carnation, I'm only making one choice. I'm not choosing 2 things. I'm making one choice out of different categories, but it's only one choice. So I'm not multiplying anything. In fact, remember that or in probability means to add. But and in probability means to multiply. So what is the probability that the first flower we choose is a rose? Well, it's simply we count how many roses we have. Well, I know it's 10. Out of how many total things, how many total flowers, there are 60. So that's the probability of choosing the first rose. Now, we have the rose and we put it back in. What is the probability that we choose a rose again? We're choosing 2 roses, just one after the other. Well, there's still 10 roses and still 60 flowers. So we get the same probability both times. Now, kind of a reminder, I like leaving my probability in unsimplified fractional form because it shows me how I got the answer. But if you really need to keep going, just plug into the calculator, get your decimal answer, and you see that the probability of choosing a rose, putting it back with replacement, then choosing another rose is about 3%, a little bit less. Let's do a very similar problem. What is the probability the florist chooses a rose, keeps it, we call this without replacement, then chooses another rose? So let's start. With the first rose, the probability is 10 out of 60. Now that rose is gone. It's no longer part of the collection. So what is the probability of choosing another rose now that one is gone? We simply determine how many roses we have left, 9, and how many flowers we have left, 59. So 2 ideas. multiple events, we're choosing two things. We would multiply two things together. But let's also talk about independence. Notice that the first row's the probability is 10 out of 60. Always if the first thing we choose is rows. If we replace this rows, the probability of choosing a rows remains the same. The probability does not change. We say the events are independent because the probability stays the same. But what happens down here? The first rows is still 10 out of 60, but if I don't replace it, then the probability of the second rows is no longer the same. And we'll talk about this more in the next video when we talk about conditional probability. But let's go to some more advanced problems. In this one, the probability that a newborn lion will survive to 1 year old is approximately 0.324. We can assume these events are independent for this problem. What is the probability that 3 randomly chosen newborn lions will survive their first year? Do we have multiple events? Are we choosing multiple things? Of course, I tell you plainly 3 things, which means we should multiply 3 things together. So the probability that 3 survive is the first one and the second one and the third one survive. We're multiplying. So the probability that the first one survives is 0.324. And then the second one survives is also 0.324. And then the third one survives is also 0.324. Now, when you get comfortable with doing probability, knowing what's going on, I could have just started by writing 0.324 cubed. But I do want you to see where it comes from. And then if I type into the calculator, I get 0.034. But the main point is understanding what's going on. There's one other side note here that's not going to make as much sense until the next part, but when I do probability problems and I write my answers, I put things in order, meaning the first thing I write is always going to be my first choice. That is the probability of the first thing happening. The second thing I write is going to be the probability of the second, etc. And that helps me see and understand and organize what's going on. For example, when I do the next part, what is the probability that the first 3 out of 7 chosen will survive? Do we have multiple events? Sure. How many events do we have? If you said 3, that would not be correct. We are choosing 7 things. Since we have 7 choices, we should be multiplying 7 things together. So what is the probability? Well, let's do these things in order. So the first one survives. The probability is 0.324. And same for the second one. And then same for the third one. Now the fourth one does not survive. So the fourth number I should write should be the probability of not surviving. Well, what's the probability of not surviving? Isn't that the complement of surviving? That is 1 minus 0.324. So the probability of not surviving is 0.676. So as I wrote it, that means that the fourth line did not survive. Now the fifth thing I write represents the fifth line not surviving. Same for the sixth and for the seventh. Which could have been written like this: 0.324 cubed times 0.676 to the fourth. Hey, if you understand that that's the main thing, because the final answer is simply type into a calculator, that is not the most important part. The most important part is really the setup. All right, let's take a look at a more complicated appearing problem. Same probability, still talk about the lions. What is the probability that at least 1 out of 5 will survive? So at least 1 means it's really the probability that 1 survives, or 2 survive, or 3, or 4, or 5. This is a very, very complicated problem. Let's just look at the probability of 1 surviving. The probability of 1 surviving could be something like this. It could be that the first one survives and that the next 4 do not, right? Or it could be that the first one does not, the second one does, and then the next 3 don't, or etc., etc. Do you see how complicated this problem is just to find the probability of 1 surviving? Now we have to do for 2 and 3 and 4 or 5 and add these all together. Isn't there a much easier way to do this? Well, I certainly hope so. Let's see if there is. Instead of finding the probability of 1 or 2 or 3 or 4 or 5, I'm going to find the probability that none survive. So the probability that none survive is the first one doesn't, the second one does not, the third, the fourth, the fifth, all do not survive. So I get 0.676 to the 5th power, which is about 0.141. Is that the answer that I want? Well, no. So why did I do that? Well, it's because the probability of 0 is what? Well, isn't it the complement of 1 or 2 or 3 or 4 or 5? So the answer I want is not the probability of 0, but 1 minus the probability of 0. So my final answer is 1 minus 0.141, or about 85.9%. Let's look at one more problem. And I'm going to use this problem to illustrate a way that I organize things to help me solve problems. You don't have to do it. It's simply going to be a way that makes problems less complicated for me. And it's going to be the second part of the problem. So here, the weather forecast says that there is a 70% chance of rain on Monday, the first day, a 60% chance of rain on Tuesday, and a 20% chance of rain on Wednesday. What is the probability it will rain all 3 days? Well, we have 3 events, right? 3 choices, which means we should multiply 3 things together. And of course we will. It's the probability that it rains on Monday times the probability that it rains on Tuesday times the probability that it rains on Wednesday. And once again, the numbers I put are in order so I know what's going on. So we get 0.7 times 0.6 times 0.2, which equals 0.084. It's about an 8.4% chance it'll rain all 3 days. Now, what is the probability that it will rain 2 of these days? And we say 2, exactly 2 out of the 3 days. So when I'm doing things that maybe I'm not sure how to find the probability for, and there are 2 or 3 things, I very often use a tree diagram. I like a tree diagram to help me organize it. So how many things am I choosing? Well, I'm not choosing 2. It's 2 out of the 3. So really 3 things that I'm choosing, but I want 2 of them. What do I mean by that? Okay, let's start doing a tree diagram. So these are what we call branches. So the first branch is going to represent my first choice, or in this case, my first day. And I'm going to put rain on the left side and no rain on the right side. And that's for Monday. Now I'm going to do branches again. So for rain the first day, what's the probability that it rained the second day on Tuesday? Well, I'll put rain on the left and no rain on the right. But it's the same as if it hadn't rained the first day. So I can put extra branches over here. 0.6 rain on the left, 0.4 no rain on the right. So the second level of branches is my second day or second choice. And then my third day, Wednesday, I'll do one more level of branches. And you can see that when it gets to be too many levels, this problem gets really complicated. The picture gets really messy. But again, I'm going to put rain on the left, no rain on the right for all of these. And it might seem like a lot of work to do, but I find that in the end, it makes solving the problem much easier for me. Now, let's answer the question, which is, what is the probability that it will rain 2 out of these 3 days? So let's draw colors down these branches. I'm going to put it in red. That are going to represent rain 2 out of the 3 days. Well, this is rain, and then down the right side is no rain. So that represents 2 out of the 3 days. If I had gone rain, rain, and then down the left side, that would have been 3 days, so I don't want that one. Now let me change to blue so we can see another thing. What if I started here and went to say rain, yes, no rain, right? Down the right is no rain, but then back down the left. Isn't that rain 2 out of 3 days? Can you find any other branches through all the levels that give us 2 days of rain? What if we went no rain, then rain, then rain? That will give me 2 days of rain out of 3. Go on and convince yourself that there are no other ways, no other paths that give us rain 2 out of 3 days. Okay, so now, how do I find the probability that I want? Well, it's the probability of the red path, if you would, where we have 3 things we need to multiply, right? I could do 0.7 times 0.6 times 0.8. That's the red path. Rain, rain, no rain. Or it could be the blue path, which is rain, no rain, and then rain again. Or it could be the green path, which is no rain, then rain, then rain. So it could be either the first one or the second one or the third one, and I emphasize or because I know that means to add each of these individual probabilities together. So we could continue. If we really want an answer, we could do 0.7 times 0.6 times 0.8. So the probability of the red path is 0.336. The probability of the blue path, 0.7 times 0.4 times 0.2, is 0.056. And then the probability of the green path is 0.3 times 0.6 times 0.2, which is 0.036. And to get the total probability, we simply add these 3 pieces together. giving us a probability that it'll rain 2 out of the 3 days as 0.428, or a little bit less than a 43% chance.